Alrighty, good morning, everybody. Let's go ahead and get started, shall we? Let's see. First things first, while I haven't had too much time to look at it just yet, I was able to see the average of your first exam. Looks like the average for the exam was just about 80%, which is pretty standard for the first exam. Just remember your grade on Canvas. Like, you're gonna want to look at your percentage for the exams. If you look at just the exam score itself, you'd want to divide that by 75 in order to see your percentage. So that corresponds to about 60 out of 75, which is 5 questions missed out of 30. So, if you did not do as well as you liked, make sure that you're taking advantage of all the resources that you have. The textbook has quite a few problems. There are practice exams up. Just kind of maybe doing the homework before Sunday night. Just having time to have it go through your head. Make sure you're checking the answer keys for the homework as well. Those are all on Canvas, so just ways to help you guys out. So if you're not getting something, ask questions. We'll do another review thing before our next exam, although we will also have a review this Thursday for going over things that you got wrong, if you want. But it looks like most of you did pretty well, so I'm not too concerned. Also, I've now made it so you guys can see the correct answers as well as what you put, so you'll be able to go into your exam and see. Good morning from your car. Oh goodness, I hope it's not too cold out. Or I also hope you're not driving, but we'll see. So cool. Yeah, just take a look, see what you did wrong. If you did get things wrong, see if you can, figure out why they're wrong, and see if you can't work through the problem to find the correct answer. There were a number of students who got 100%, so there's not going to be any adjustment this time. So we'll see what happens for the next exam. So, awesome. Alrighty, so we left off kind of towards the end of talking about the idea of moles. And so, we talked last time about, the concepts of molar mass, which was going to be the sum of all the atomic masses for a compound. We can let's just kind of go through that again. If we wanted to find, for example, the molar mass of this particular compound, which is called sodium sulfate, we can do that. We can say the molar mass would equal 2 times the atomic mass of sodium plus the atomic mass of sulfur plus 4 times the atomic mass of oxygen. Notice how these subscript numbers here again tell you how many of that particular element you have in your compound. So you'll be using those in your molar mass formula. So if you were to look those up on the periodic table, or if you have been teaching chemistry for a number of years, you have them all memorized, unfortunately. At least these ones. You can do it that way too, of course. There's definitely no need to ever memorize that. You will have a periodic table, so yeah. These numbers do come from the periodic table as well. They are the atomic masses. Those 3 numbers all come from the periodic table. So let's go ahead and do the math. 2 times 22.99 plus 32.07 plus 64. That equals 142.05. Apparently we're doing it in light blue, which is cool. We don't have to worry about sig figs for these. Just leave your answer as it is. Ah, awesome. Sounds good. That's what I care about. Safety first. Okay, cool. Um, that's awesome. That's pretty good dedication too. So, cool. And I guess it makes sense with your handle being Rover chick, right? Maybe if it is Rover, or it could be River, I guess. But you're on the move. Okay, cool. That was really awful. Never let me do puns like that again. That's. Oof. Anyways. So yeah, that's again how we would deal with our molar mass. Units of that are grams per mole or AMU. And so we saw last time we can use this as a conversion factor. There were some questions on your exam about using molar mass as a conversion factor. But just thought I'd recap it before we moved on here. So we could say that if we had 10 grams of sodium sulfate, we could go ahead and see how many moles that would be. Right? We can use this molar mass as a conversion factor, as we should. So we'll take our 10 grams. Notice that we have grams and moles here. We're going to want to put grams on the bottom along with the number that goes with it. So that's our molar mass. And we're going to put 1 mole on top. Let's go ahead and do the math. 142.05. We get 0.07039777, whatever. This time we do look at sig figs. We have 3 sig figs in our starting number. You don't have to worry about the sig figs for your molar mass. So let's just look at the starting number. We have 3 sig figs there. So we're going to want to make sure that our answer has 3 sig figs as well. So we're going to round that to 0.0704. And that would be moles of sodium sulfate. We'll learn how to name these in a few chapters. So you're not expected to learn them quite yet. With that in mind, we could also do some other things. We could see, okay, well, we know we have that many moles of sodium sulfate itself. We could also see how many moles of sodium atoms we have. We can do that. How many moles of sodium do we have in that particular sample? We can do this by looking again at our kind of chemical formula for it. Remember that this means you have 2 sodiums, 1 sulfur, and 4 oxygens per unit of sodium sulfate. So if we know we have 0.0704 moles of sodium sulfate, and we know each one of those has 2 sodiums in it, we're just going to see that it's going to have twice as much, right? Let's go ahead and do that. So if we start with our moles of sodium sulfate, we can use as a conversion factor how many atoms of sodium there are per unit of sodium sulfate. We know that there are 2 sodium atoms for every 1 sodium sulfate unit. I'm tempted to say molecule there, but that's not quite right. We'll go over that in chapter 5b, why that's not right. But for now, I'll have to say unit. So, cool. And so doing that, we're going to get... I can do this part in my head. No, I lied. No, well, we can round, I guess. Yeah. Okay, cool. By doing that, we'll have twice as many moles of sodium as we do of sodium sulfate. And if we were to look at oxygens instead, we could say, oh, we have actually 4 times as much for our oxygen atoms. So we can kind of piece together little bits out of our various formulae for our chemical compounds. Let's see, how about another one? Why don't we do, how about we take our glucose. Let's see how many oxygen atoms are in 125 grams of glucose. So that's of course glucose here. I'll just go ahead and give us the molar mass for glucose. Common enough compound. But of course you would get that by adding 6 carbons, 12 hydrogens, and 6 oxygens. So let's go ahead and work through this. Remember that the molar mass there of 180.2 grams per mole is also the same thing as saying 180.2 grams per Avogadro's number of molecules. Right? That's what a mole means, right? So it's a number of molecules. So or atoms or whatever we're looking at. In this case, it's telling us for that many glucose molecules, we'll have 180.2 grams. And so we can use this to our advantage in order to see how many molecules we have in our sample. And since we're asked for how many oxygen atoms we have, we're going to use our chemical formula to go from molecules of glucose to atoms of oxygen. And this is just going to be another unit conversion. There's really nothing different here. So let's go ahead and set it up and see how this works. So let's start with our 125 grams of glucose. That's what we're given to start. First, we're going to convert into molecules. So from grams, you can convert to moles or molecules. That's pretty much all you can do. You could convert to moles if you want. It would totally work. And we'll take a look at what that would look like in a second. In this case, let's go ahead and put our Avogadro's number on top. Make sure that you understand also why we can generate this conversion factor. So 180.2 grams per mole is the same thing as saying it for that number of glucose molecules. From there, we know we have 6 atoms of oxygen for every glucose molecule. We know this because, oh my goodness, there it is. That's the number that follows oxygen in our chemical formula. So that tells us we're going to have 6 atoms of glucose, or 6 atoms of oxygen in every molecule of glucose that we have. And so we can go ahead and do the math now. So we'll have 125 divided by 180.2 times Avogadro's number times 6. Doing that, again, I'm still in light blue somehow. We get 2.51 times 10 to the 24th atoms of oxygen. So we can do all sorts of crazy fun stuff with this idea of moles. So we can go from grams to atoms of a particular number of particular atoms in a compound. We can go from grams to moles of a particular atom of a compound. So we can do all sorts of good stuff with it. Rest assured you'll have some homework on this, so you'll have plenty of practice working through it. So yeah, there we go. So we're actually now going to work on kind of doing the opposite process by trying to see if we have information about the number of atoms in a sample of something, we're going to see that we can come up with the chemical formula. But first, we're going to look at one more kind of aspect of this. That, something that's actually pretty useful for you guys. So, we can also see the mass percent of an element in a compound. And so we're going to see that, if you're looking at your, sodium intake perhaps, or you have a patient who's looking at their sodium intake, pretty common thing to be looking at. Often, it's actually impossible to take pure sodium and throw that in your food and, have it work out that way. Most of the sodium comes from salt, right? And salt is a compound that contains the element of sodium. And so we're going to see that we can figure out, by looking at a mass of salt, how much sodium is actually in there in terms of mass as well. So we're going to see that this is going to kind of follow a formula. And we're going to see that it's going to be the mass of the element, whatever you're looking at, times the number of atoms of that element. So, for example, for glucose, that would be 6. If you're looking at oxygen or something, we'll do some examples so you can see. And that would be the molar mass of the compound. And actually, I'm going to go ahead and I'm going to just change this one. Let's say it's the number of that element in the compound. So let's look at it for sodium chloride. So if we want to see the mass percent, I guess since this is also a percent, we're going to multiply it by 100%. That'll be there as well. So if we want to see the mass percent of sodium in sodium chloride, we can do that. We're going to need the atomic mass of sodium. Let's go ahead and pop open our periodic tables here. And we're going to find sodium. It's over here on the left side. There it is. We see we have 22.99. This is going to be our atomic mass. We see that we have 1 sodium atom per sodium chloride. So that's just 1. And then the molar mass of the compound is going to be the 2 atomic masses put together. I guess if we were to look up chlorine, we would do that. We'd say, okay, here it is on the right side. We'd click it and see that it's 35.45. And that's where that number comes from. And so we would just do the math. So 22.99 divided by 22.99 plus 35.45. Let's put some parentheses in there. By the way, I do have a suggestion for those of you who may have not done so well on the exam. Make sure that you're going through these problems as we do them in class. Just make sure that you can use your calculator. All calculators are different, right? So make sure that you know how to use your calculator to get the correct answer by using these numbers. So doing that, I guess I have to put our times 100%. We're going to get 39.34% there. So this tells us that if we have, let's say we have a 25 gram sample, how many grams of sodium do we have? We can do that. This mass percent we can use to figure this out. It's simply a matter of multiplying them together. So we can say that we have this 25 grams sample of sodium chloride. We know that sodium chloride is 39.34% by mass sodium. So we can go ahead and do this. And doing so, we get 9.83 grams of sodium. Notice the units are just going to stay the same as what we had. Percents don't have any units, so it's just going to be grams that we're left with here. We could also use this information to go the other way. What's the, let's see, recommended sodium intake? Let's see. Okay, Americans, so blah, 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 limiting to 2,300 milligrams. Okay. So, 2,300 milligrams. Let's see how many grams of sodium chloride is going to contain that much sodium. So that's our daily suggested limit. Although Americans tend to go a little heavy, myself included. I love salt. But shame on me. I'm going to die of hypertension. So, well, I guess of complications thereof. So, but I'll be happy when I die of that. So, alrighty. So, looking at that, we know that we have 2,300 milligrams. We can go ahead and notice that our answer wants it in grams. So let's go ahead and make sure that we can convert this to grams first. We know hopefully now how to do that. That's our unit conversion, right? Just from grams to milligrams, or vice versa in this case. We know that last time, in order to figure out how much sodium was in our sample, we had to multiply our sample mass by the percentage. In this case, because we have the sodium already, we're going to do the opposite. We're going to divide this time. So let's go ahead and divide this by our percentage. Remember, if you're going to use a percent mathematically in your calculator, you would actually input it as 0.3934. Remember, percentages, you'll always shift the decimal twice over. If you do that, let's say our 2,300 times 10 to the negative third, so 2.3 is what we're going to have here. We divide that number by 0.3934, and we end up getting 5.85 grams of sodium chloride. So we're just doing the opposite process of what we did last time. And so we can say that this is the amount that we should be having per day, not any more than that. So for salt itself. For sodium, it's of course it's a smaller number. Cool. Any questions on that? Alrighty. Let's do another example. Let's go back to our glucose. And let's go ahead and see if we can't get the mass percent of oxygen from that. So, thankfully, we still have our molar mass from before. Yep, that's all right. That's what we're going to be doing practice for. Hooray! So let's go ahead and do it again. So, the mass percent of a particular element, remember, is the atomic mass Let me put the chemical formula here for you guys. Times the number of oxygen over the molar mass of the compound. So let's go ahead and see these numbers. Excuse me. Atomic mass of oxygen, we'll get that, of course, from the periodic table. Off we go. Here it is, periodic table. We find oxygen. It is up here. Here it is. And we end up with 16. If you really want to use that number, go ahead, but 16 works just fine. So that's going to be 16. Oops. Not 4 o'clock in the afternoon. 16. We have 6 oxygen atoms from our chemical formula. Again, that's where this number here is coming in. All right, and then we have our molar mass on the bottom. And of course, we'll take our percentage bit there. So let's do the math. 6 times 16 divided by 180.2. Doing that, we end up with 53.27%. And so while this one may not be as useful, perhaps, as the sodium in sodium chloride, it's still a valuable exercise. As we're going to see, we're going to be doing the opposite process pretty soon. So it's going to be a good idea for us to practice this first. Not really. These are all just theoretical things. So I usually just leave it as 4 sig figs or 2 decimal points. Since these are not measurements, they will not carry sig fig information. So these are just theoretical percentages. Good question. So you get a short break from sig figs for a bit. I think you'll be happy about that. Of course. Cool. Alrighty, let's do another one. Let's go ahead and do one kind of from scratch. I don't know. Let's say we have something that is, how about we take formaldehyde? Which is CH2O. Let's say that I want to find the mass percent of hydrogen. Gonna sneeze again, maybe? That's the worst feeling. I hate it. Don't you guys ever hate when you have to sneeze, but it just never happens? The worst. Okay, so for this, we'll have our mass percent formula. Will be the mass of hydrogen times the number of hydrogen per formaldehyde molecule. And then we would have the molar mass of our formaldehyde underneath it, times 100. So we have a couple things to look up here. We're going to need the mass of hydrogen. We're going to need to count how many hydrogens per molecule we have. And then we'll need the molar mass of our compound as well. So one of these we can do right away. We know that we have 2 hydrogens, so that's going to be our number there. If we look up on the periodic table, we'll see that hydrogen is 1.008. And now our molar mass we'll have to calculate, so let's go ahead and do that. So that's going to be carbon plus 2 hydrogens plus oxygen. If we look those up, we'll find these numbers, which we can go ahead and add. So 12.01 plus 2 times 1.008 plus 16. We do that, we get 30.03 grams per mole. Alrighty, so again, make sure you can find these on the periodic table as well. That's always a good exercise. Make sure you can find carbon, on the periodic table. So definitely take some time, pause the videos when you're watching them and, say, oh, okay, I can find carbon and I can find that it's not silicon. Whoops. I can find that its molar mass is 12.01. You can do these things. So make sure that you are, totally able to do all that stuff. So although we may go a little faster in the lecture itself, just in the interest of time, make sure that, you have total freedom to stop it and pause it and, make sure that you can do it before moving on. So cool. So now that we have that number, we can go ahead and figure out our mass percent. So that's going to be 1.008, which is our atomic mass of hydrogen. We have 2 of them in our compound. And then we have our molar mass at the bottom. And we'll throw in our 100% as well. So let's go ahead and do the math here. 30.03. All right, and I get 6.71% by doing that. And so again, I usually just leave this as 2 decimal points. That's definitely enough information there. So hooray! We can figure out the mass percent of something in a compound. All right, so I mean, if you really wanted to see how to put this in words, I guess we can say that formaldehyde is that many percent of hydrogen. So there you go. There's your party trick for the day. So you can do that. We're going to see, however, that more useful is going to be going the opposite way, figuring out the chemical formula of something from experimental data, which is definitely something that was done many, many, many times over 200 years ago. So how people figured out what the formulas were for all these compounds. So, hooray. Alrighty, any questions on those ones? It's pretty much, just a formula, I suppose. But still a good thing to practice. Alrighty. In that case, let's do it in reverse. We can totally do this stuff in reverse by taking percentages and then figuring out what the chemical formula is going to be from there. We're going to see that this is called finding out the empirical formula of a compound. And what the empirical formula is, it's the smallest ratio of elements in a compound. So for example, if we take our glucose, we're going to see that this is what's called a molecular formula. And it's different from an empirical formula because it is not the smallest ratio. In fact, we could say the smallest ratio for this would be this. This would be an empirical formula. Which we can see is a smaller ratio. It's a ratio of 1 to 2 to 1 for carbon to hydrogen to oxygen. For glucose, it's 6 to 12 to 6, which is the same ratio, but it's bigger. So we don't call that an empirical formula then. We would call that a molecular formula. So we're going to see that many compounds might share the same empirical formula. So for example, formaldehyde, which we saw was just CH2O, shares the same empirical formula as glucose does. We're going to see many other carbohydrates also follow that same kind of pattern. So there we have it. So we're going to see that we can use experimental data, something that would be given to you, of course, to figure out what that smallest ratio is going to be between those. And just if we look at this formula, that tells us we have 1 carbon to 2 hydrogens to 1 oxygen. That's what the empirical formula tells us. And so we can go ahead and let's take a look at an example, and we'll see how to do this. So let's say a compound, or rather, we'll say a compound is made of 15.8 grams of carbon and 84.2 grams of sulfur. So this is experimentally determined. Someone burned this thing and figured out how much mass of each of the elements that we had there. We cannot use masses directly. We cannot compare different elements by mass. Not going to work. The reason is because they would weigh different things, right? We have no way of saying, okay, 84.2 grams of sulfur is, twice as much as the carbon. No, it doesn't work that way. We can't use masses directly. So what we can use, however, is the number of atoms that would be present in that mass and compare those. Or what's a little bit easier is to use the number of moles instead. So let's go ahead and do that. If we convert both of these numbers into moles, let's see what we'll get. So 15.8 grams of carbon, if we convert that to moles, we're going to want to figure out the molar mass. Here's carbon, 12.01. So we know that carbon is 12.01 grams. Moles will go on the other side. Let's just do this real quick. 15.8 divided by 12.01. We get 1.31557, whatever. Let's just leave it there. That's moles of carbon. If we now do the same thing for sulfur, we'll go ahead and look up its atomic mass. We've got to find it first. Here it is. Sulfur's over here. We see it's 32.07. Doing the math. 84.2 divided by 32.7. We get 2.5 749 ... Who cares about the rest? And so now we'll want to compare the two. So once we have them in moles, we can compare them, right? Since moles is just another way of talking about a large number of atoms, we could say roughly we have 1.3 moles or atoms of carbon for every 2.57 atoms of sulfur. We can compare these now that they're in moles. And so if we wanted to find the lowest ratio of them, we would just divide each number by the smallest number present. And we'll do this plenty more times today. And that's how we'll come up with a ratio, right? So if we take this and divide by 1.31, let's just say 1.31. If we divide this by 1.31 also, oh, you know what? I forgot a 0 in my original number. This number is a little bit off. It's 2.6255. Okay. If you can see here, we end up with 2 as our number by dividing both sides by the smallest number that we had there. And by doing so, this tells us we have 1 carbon for every 2 sulfur atoms. And so we would go ahead and write the empirical formula as CS2. You'll just write them in the order that's given to you. So we did carbon first, so we'll put carbon first in our compound. So the point here, you can't compare mass directly, but you can compare moles directly. Once they're in moles, it's kind of the great equalizer of chemistry. Moles is the only way to be able to compare different elements or different compounds. So we're going to see that we'll be doing this quite a bit throughout chemistry, so you'll want to get very familiar with this idea of moles. So it's nothing scary, it's just a way of talking about a very big number in small terms. So let's do some more. We're going to see the process is going to be exactly the same for all of them. So here's another example. Let's say we have one that is, 20.0 grams of carbon, and 3.35 grams of hydrogen, and that's going to be 26.65 grams of oxygen. These ones I can't make up in my head, by the way, because I have to make them work out, right? So I do have a finite number, but I have like 10 examples. So if we really want to keep going, I have plenty more we can do. So let's go ahead and kind of set these up. We're going to want to convert them all to moles. And then after that, divide by the smallest number of moles. That's really all we're doing here. So let's go ahead and do it. So 20 grams carbon. I'm just going to set all the numbers up so I don't have to keep scrolling up. And then we had 26.65 grams of oxygen. Okay. So we're going to want to convert all of these guys into moles. We would do that by looking up their atomic masses. So for carbon, that was 12.01. For hydrogen, it's 1.008. For oxygen, 16. All of these, again, are from the periodic table. So let me just indicate that again, just in case. These are just the atomic masses. So those are all from the periodic table. It just so happens that because I have these memorized, it's a little faster. But don't worry, take all the time you need on these. this is a good way to kind of get familiar with where some of these atoms and elements are on that table. So very useful skill. Okay, so let's do it. So 20 divided by 12.01. We get 1.66. Or whatever, we'll throw one more in there. If we take our hydrogen, 3.35 divided by 1.008, we get 3.32. And then for oxygen, we can do that one as well. So 26.65 divided by 16, we get 1.665. And hopefully right away we can see the pattern here. But just to be sure, let's go ahead and divide by the smallest number. If you do that math, you end up getting 1, 2, and 1. Which tells us, since these were the elements that gave those numbers, how many of each we have in our empirical formula. So we're going to have 1 carbon, 2 hydrogens, and oxygen. So this could have been glucose. It could be formaldehyde. It could be any number of other sugars that we can deal with. So the empirical formula just tells us what the smallest ratio is. So in order to find out the other one, we'll see that there are other ways to do that, which we'll talk about probably tomorrow. So today we'll just do more of this stuff. All right, questions on that one? All right, so again, this is all we did. Yeah, hopefully not too bad. Let's just up the ante a little bit. So sometimes you will be given the mass percent of an element. No, I know how to spell, I swear. No, I don't. Element, there we go. Instead of a mass. For example, here's one. I've got a problem here. So we have 28.03% magnesium, 21.60% silicon, 1.16% hydrogen, and 49.21% oxygen. So, if we're given percentages instead of grams, I think the easiest thing to do is just say, okay, if we have 100 grams of this compound, and if that compound is 28.03% magnesium, well, that just means we have 28.03 grams of magnesium, right? And so, here's the solution. Erase percent and write grams instead. Ta-da! Because these are all mass percents, we can just say if we had 100 grams, the percents would be equal to the masses. So, hooray. Just do that. Makes it easier. I mean, if you really were crazy, which is totally fine, you could choose any mass you wanted. Say you had 5 grams and you could multiply 28% times 5 grams and find out some new mass, but way easier, just assume you have 100 grams. Ta-da! No thinking required. So, now that we have that, we can go ahead and do the same thing here. Let's see what we get. I'm gonna just erase this big old comma here. Some of these I don't actually have memorized. It's awesome when we see that. So oxygen we do have, hydrogen we do have. All these are going to have 1 mole on top. Let's go ahead and look up these molar masses. Atomic masses, either way. We have magnesium. It's up here in the top left-ish area. It's 24.31, we'll say. For silicon, we'll find that one next. Silicon is kind of in the right side. It's over here. Silicon is going to be 28.09. So let's just go ahead and do this fun stuff here. 28.03 divided by 24.31. We get 1.15. I'll fix that. For the next one, 21.6 divided by 28.09. 0.769. If we do the hydrogen, 1.16 divided by 1.008, we get 1.15. And then now the oxygen, 49.21 divided by 16. Do that, we get 3.07. Close enough. All right, so we found all their moles, so we're going to want to divide by the smallest number. So we'll divide all of them by 0.769. That's obviously 1, but let's see what we get here. I already have oxygens up, so let's do that 1.769. We get 3.999. If we take our 1.15 divided by 0.769, we get 1.495, and that'll be the same here. So, what do we do in this situation? Obviously, this can be rounded to 4. That's not a problem. However, we have something that's 1.5, pretty much. What do we do with that? Well, we can't just round it to 1, and we can't round it to 2 either. I mean, it's kind of smack dab in the middle. So, if we were to just write this as is, we would say we have 1.5 magnesiums, 1 silicon, 1.5 hydrogens, and 4 oxygens. That's really ugly. Let's never do this. However, we could see that, oh, I know, we can get rid of those decimals by just multiplying everything by 2. So we have something that has 0.5 in it. If we multiply everything by 2, we'll still have the same ratios, but it'll get rid of these horrible decimals that we have. And doing so, we'll get Mg3, Si2, H3, O8 by putting all of that together. So this gets rid of those pesky decimal numbers. So we're going to see that there's kind of some handy rules here. So if after dividing something that ends in 0.25, you should multiply your whole thing by 4. So this would be your empirical formula here, the Mg3, Si2, blah, blah, blah. Because we want the smallest integer numbers. So putting it with 1.5s is not gonna cut it. So if your number ends with 0.25, you'll multiply by 4. If you end up with something with 0.33, you'll multiply by 3. If it's 0.5, you'll multiply by 2. 0.66, you'll go by 3 again, and 0.75, you'll go by 4. So if you are, when you divide, you notice that we had 1.5 here. That's why we're going to multiply by 2 to get rid of those. So we're going to see if you end up with any of these numbers, you'll want to multiply by a constant to get rid of any decimals. We cannot round. We cannot round numbers in empirical formula. Unless it's something that's like 0.95 or 0.05 or something really small like that, where it's very close to the whole number, that's when we can round. Other than that, we're not going to round. We're going to multiply by something to get rid of our decimal instead. So we'll see a couple of examples where maybe we'll have something like this tomorrow. But just understand that you cannot round. So if we get 3.999, yeah, that's 4. That's not a problem for rounding. That's pretty obvious for us. But if it's 1.5, we can't say, no, it's not 2, it's not 1. We're going to have to multiply everything by 2 to get rid of it. All right, so that's going to kind of be our like handy-dandy cheat sheet. I guess we could add a couple more. If it's, 0.16, you could multiply by 6. That would be another thing you can try. You can also just try multiplying by various numbers, see if you can get integers out of them. There's no need to memorize this table or anything. So, all right. So tomorrow we'll continue with this sort of thing. We'll see how to figure out a molecular formula from an empirical formula, and we'll do some more practice with this. So I'll see you guys tomorrow. We'll continue on, and then Thursday we'll have a review for your exam if you like. If you do want to do a review on Thursday, in Discord you're going to have to put screenshots of your questions. Just because you can't just say, question 15, can we do that one? Because your question 15 is going to be different from everybody else's question 15. So it's better for you to just take a screenshot of it or something and just share the question directly in that Discord, in that review questions area. So I would do that. All right. With that, I'll see you guys tomorrow. Have a great day. Enjoy your Tuesday. I'll see you tomorrow.